So,
Okay.
okay, I think we have done a few things over servo motor last time through the ES32. So we are going to do the mostly similar kind of things with STM32. How it is different. But right now we are also dealing with the FreeRTOS thing, right, along with our peripherals. So here, like if we can, for the general purpose, mostly whenever we want to control a servo motor, this was our manual method in which in a while loop we can set different kinds of angle and duty cycle for the servo motor, right? But in this thing you can easily see that it is consuming different kinds of delay, right? And along with, if we are running this everything in a while loop, that means other program will not we cannot run other programs like other 5 to 6 tasks, because the program is continuously running in this program even with a very small delay. Okay, so this is the general purpose method, right? But how you can also see some exact number like halt delay 50 is called 72 times per sweep cycle. CPU is blocked for 3.6 second total per sweeping. Okay, nothing else can running during this time. That's why, because our other tasks are stuck here. So that's why what we'll do this things, send the same thing with the FreeRTOS. In the FreeRTOS, we will not use the halt delay. We'll use V task delay. Okay, and so that our CPU can be free for other tasks. Right? Yeah, the concept of PWM and servo motor. Okay, so for PWM, like PWM, I think visuals is not correctly. Let me give you one new idea how we can use the PWM. Like how you can understand. You should try this thing on Cloud AI. Okay, let me show you. If I say the cloud that visualize the PWM to make it understand. I think I should already have shown you.
Pawan, now, sorry for the late. Did I miss anything?
Praveen? Okay, Praveen, no worries.
Yeah, yeah.
What was in the lunch?
Yes, chicken curry.
Chicken curry. Okay, nice.
Yeah, yeah, yeah.
Okay, so let's understand the PWM thing. Okay, so this is the, let's say if we increase the duty cycle, that means we are reducing the width of the pulse, right? This is our 0 to 5 high signal, right? That means our signal will remain high for this much of time. This is our time. This blue line is our time, and that means our x is time, y is our voltage. So that means our 5 volt will remain, let's say for 1 second, and then 1 second it will off, then we can reduce this timeline, right? We can do it in microsecond. So if we increase the duty cycle, that means we are reducing the width of pulse. Now you can see that our let's say if we are blinking LED or motor whatever, so let's say our motor will get 0.1 microsecond high signal, and then it's keep it low further until time again it will get high signal. So if we are changing the duty cycle, we can adjust like this, right? If we are changing duty cycle, that means we are changing the width of our signal. And if we talk about the frequency, that means number of pulse we can increase and decrease within the timelines. So that, like this, if we increase the frequency, then our motor will go high, low, high, low, high, low in the same timeline. Like if let's say we have from 0 to 5 second here. So the 0 to 5 second, our motor or bulb or LED will go high, low in the same timeline like this, right? And if we increase our pulse width, right? Then in the same timeline, our motor will, bulb will get maximum, mostly higher. And now it's look like a DC. That means we have 100% duty cycle. It's look like a DC signal, DC voltage, right? Because there is no low signal. Got it? You can also see that those numbers here. Okay, so I hope Claude helped me to to visualize the same thing in very interactive way. You can also use it in the Claude, right, for the different kinds of things to understand. So this is the level of AI right now is happening. Fine, let's back to our theory part. So here, if we want to move our motor 90 degree, then we'll give the pulse for 500 microsecond. If we want to move it for the 90 degree, then we'll go every pulse, that means for 1500 microsecond, the pulse that we are just modifying that pulse. That's why we call it pulse width modulation, right? Pulse width, that means we are modulating its width. Pulse, this is the pulse, it is its width, and we are modulating that. That's we call it pulse width modulation. Okay, this is the formula to calculate the pulse, that formula equal angle 0 to 180 to pulse width modulation. This is the timeline. So pulse equals to 500 plus angle into 2000 divided by 180. So time it is setting for 1 microsecond could be like in this manner. For pre-scaler, we can, pre-scaler should be like this 63, and our AR register should be that this much 9999, and the CCR pulse value in microsecond directly. Okay, and our hardware connection would be like this. Ground, there is a very easy connection for servo motor, you already know that. We'll give the ground to our servo motor's black wire, we'll give VCC to its red wire. Hardware connection, okay, give it a 5 volt, not 3.3 for now. Then orange wire would be our PA8, that means A8 पर आपको connect होना चाहिए. You can see in this image PA8, we can find it. Here is it, right? This 23 number pin is PA8. We can also connect on this Arduino head of 8 pin, right? You can connect here PA8. आपको इस number पे motor connect करना है. Then servo VCC will must be 5 volt, not 3.3. Then CubeMX setup में आपको क्या करना है? चलिए स्टार्ट करते हैं क्यूबमैक्स से. फर्स्ट ऑफ ऑल क्यूबमैक्स के अंदर आपको एक न्यू प्रोजेक्ट क्रिएट करना है. क्यूबमैक्स के अंदर न्यू प्रोजेक्ट, मैं होम पे जाता हूँ सबसे पहले तो. ठीक है, आप न्यू प्रोजेक्ट यहाँ से क्रिएट करोगे, बोर्ड सेलेक्ट करोगे, ओपन करोगे. आई शुड हैव दिस प्रोजेक्ट. ठीक है, okay. So this is our project. What we'll do, we'll follow our notes. First of all, timer 1 we have to enable, and we have to select the channel number 1 as a PWM generation. ठीक है, so here we'll go. Timers will enable timer 1. ठीक है, here we'll enable channel number, sorry, not that one. Yeah, this is channel number 1 पे you have to select PWM generation CH1, that means channel 1. After enabling it, just raise it above and check the parameter setting. In the parameter setting, you should have this setting. Your prescaler should be 63, then counter mode should be up, and counter period should be this much. Okay, let me share this thing. Okay, now after that your P8 should be automatic enabled. Let's find where it is. This is the P8. Okay, it is already selected to timer channel 1. So right now we will use timer 1 as a channel 1 for PWM signal. Another thing, like timer PWM channel 1 pulse is fine. Okay, everything is fine. Now you have to enable the FreeRTOS. The FreeRTOS here. Close it. Middleware FreeRTOS version.
Kavan, your screen is freezed, right?
Sorry.
Your screen is freezed, but I can't see any movement in this in your screen.
Okay. Otherwise, like Jatin and you are facing the same issue.
No. It's, I think Rahul, no,
Maybe mine is okay.
so refresh is
Okay.
Okay. So after enabling the PWM and FreeRTOS, you can start generating the code right from the project manager. Do not forget to select this. Give it a good name. And yeah, that's all. You can start generating code. Let me open this project here. Okay, so after generation of the code, we'll set basic minimal code. In the user code begin, we have to add this inverter HDI.h, and user code private functions, and then in that we will add start servo task and start printing task. Then in the user code begin, we'll add this IO put cat to print the logs, and yeah, user code begin will start initial printing logs, and the user code begin RTOS thread के अंदर we will initiate two tasks. One task would be start servo task, second task would be start print task. Then you can fully replace that FreeRTOS.c. Right, for sake of convenience, you can directly get the code from this GitHub link. The top of the tutorial, there should be a GitHub link where you can find the code into the core and SRC. Okay, and yeah, after that, let's check our FreeRTOS.c. So here we have included HDI.h, and in the user code begin function prototype, we have defined our functions. No, not the function, we call it as a task. Right, so this is the definition of the task. This is we call declaration of the task. Okay, the definition of task, in that we are just printing this few logs. We are initializing that angle should be start from the 0, and step, that means it should be around something, it should be step from the 5. And in the while loop, we are calculating the total pulse right here. And after that, initializing that pulse, we have moved to the next step by adding the same into as angle. Now reverse direction at the limit. That means what limit we will reverse the same thing. That means our stepper motor will go from 0 to 180 degree, and then from 180 degree to again 0. Okay, and that will continuously into the while loop. Here we are adding a very small delay through the V task delay. This task is not any specific task, but just for the printing the pulse and angle for the servo motor. Okay, now let's click here, build it. Then debug as STM32 application. Okay, code is done. Let me first connect to my servo motor. What was our pin numbers? P8, I think, right? P8. This is DC. Yeah. Before that, what we'll do? Let's open the putty, and let's first of all resume our code. Yeah. After resuming the code, setting up the things in the putty. Click on serial. Select the COM port. In my case, it's 11. Baud rate would be 5 to 11 to 11. Sorry, it's not 11.500. Yes. Now let's connect our servo motor. And you can see here, this is our connection, and our servo motor will continuously move from 180 to 0. You just need to connect 3 wire, 5 volt ground, and PA8 port number P, and the number is 8A, sorry, A8.